So far we've discussed solving differential equations where the forcing function on the right-hand side is continuous. But sometimes we end up having a forcing function which is piecewise continuous. And theoretically, the Laplace transform method works for piecewise continuous functions on the right-hand side. So let's start to look at what we're going to do with those. Sometimes the forcing function capital F of t on the right-hand side of a differential equation has a description in terms of cases. So we have something like f of t equals some function f1 of t when t is between 0 and, let's say, some number c1, and it's f2 of t when t is between c1 and some other number c2, and it's f3 of t when t is between c2 and c4, and maybe it has m different versions on different intervals. So it's fm of t for t between cm minus 1 and cm. So each of these different functions that applies only to a certain interval is called a case. So f of t is piecewise continuous if the parts f1 through f1 of t through fm of t are continuous. But unfortunately, we can't use the Laplace transform method on this description of f of t. We need to get rid of the cases and write it as a sum, something like f of t equals g1 of t plus g2 of t, etc., up to gm of t. So just that with none of the for t in between this number and that number. Now there's an easy way to do this. We can accomplish this with a function ua of t defined to be 0 when t is between 0 and a, and then 1 for t greater than or equal to a. This is called the unit step function. And even though this function itself has two cases, we're going to allow that. So the graph of this function, of course, is it's 0 up until a, and then it's 1 from there on. Now we're actually going to use functions like this in pairs. We're going to use this with ub of t. So that's 0 all the way up until b, and then it's 1 after that. In particular, ua of t minus ub of t is the function so it's 0 all the way up until a, and then it's 1 from a to b, and then it's 0 again after that. So we can see if we subtract these two functions, we have 0 minus 0 is 0. Then between a and b, we have 1 minus 0, which is 1. And then after b, we have 1 minus 1, which is 0 again. So this function is 1 only on the interval from a to b. So the idea is that we can turn a function on for the interval a to b only by multiplying it by ua of t minus ub of t. So for example, the function f of t equals 0. Let me give myself more space. So I'm going to let it be 0, t minus 4, and 0. 0 for t between 0 and 3, t minus 4 between for t between 3 and 5, and then 0 again for t greater than or equal to 5. So let's graph this. So t minus 4 is this function right here. So we only want it really from 3 to 5. We want the function to be 0 otherwise. So this function can be described by it's t minus 4, and we only want it between 3 and 5. So u3 of t minus u5 of t. We're basically multiplying the function by 0 on the interval from 0 to 3, multiplying it by 1, that is leaving it alone, for the interval 3 to 5, and then multiplying it by 0 again from 5 on. Alright, so that's just one little piece. Now let's look at a function that has several pieces and see how we would write that in terms of differences of the unit step function. This pen is running out. Let me try again. So for example, let's describe the function so I want to go from 0 to 0, 0 to 2, 2, and then 2, 2 down to 4, 0. And then I want to go up to 6, 2, and then stay there. This function is actually completely continuous, but of course it has a different description on different intervals. So let's describe this. In terms of continuous functions and unit step functions without cases. So we need to figure out what these lines are here. So this first line obviously is y equals t. Sorry, that's y, the y-axis and the t-axis. So this is y equals t, and then this function, it would hit the y-axis at 0, 4. So that's y equals negative t plus 4. And then this function would hit the x-axis at negative 4. So this is y equals t minus 4. And then from here on, it's supposed to be at 2. Of course, it's y equals 2. So this function is y equals t. We want to turn the function t on from 0 to 2. And then plus negative t plus 4. We want to turn that function on from 2 to 4. And then we want to use the function y equals t minus 4 and turn that one on from 4 to 6. And then we want to use the function y equals 2 and turn that one on at 6. And then not turn it off. So this is a typical expression that we could use to describe a forcing function that has different definitions on different intervals. Definition times interval, definition times interval, definition times interval, plus definition times interval. And of course this works for, so I'm starting here at t equals 0. So I guess I should really say for t greater than or equal to 0. Now we could also write one tiny change, y equals t, instead of u naught t minus u2, we could write 1 minus u2 of t plus etc. Because if we're looking only at t greater than or equal to 0, then u naught of t and 1 are exactly the same thing. It's the function that becomes 1 at t equals 0 and stays 1. So for now we're just getting used to this step function, how we can use differences of step functions to construct a function that has different pieces and different definitions on different pieces. We're not going to use this to solve differential equations yet this week. That's on the syllabus for next week. The end.